Hi, I'm going to try and deal with structure determination of an unknown. That's like if you got something, some compound, you don't know what it is, how do you find out its structure? And before we get into the techniques, the mass spec and the infrared and the NMR, there's a more obvious way of looking into the structure, and that's by reactions. Now, before these techniques, before spectroscopy, then chemistry people would do reactions to try and work out if you've got a double bond. They'd shake with bromine water, or to try and work out if you've got an alcohol, you might use phosphorus pentachloride, PCl5, etc. So before I get into it, I just want to cover the obvious thing that in an exam they might give you reactions, and from your reactions, whether things are oxidized or whether they do other things, whether they burn and how much carbon dioxide and water they give off, those kind of common sense reactions and chemistry that we've done, that can shed light on what we've got. But the problem with those techniques is that they need quite a lot of material to do the tests. So you're going to shake with bromine water. You can't do it with a tiny fraction of a drop. You've got to have like a tea pipette squirtful in order to do your test. And that sometimes is just a lot of material. You don't have that much chemical. The spectroscopic techniques we're going to go through, they can just use small amounts of the test substance, the unknown substance, to work out what it is. So let's get into the first one of these. The first one of these is something we did back in year 12 called mass spectroscopy. Now, in mass spectroscopy, can I take you back? Indeed, the first thing I want you to do is to go back to your year 12 notes. I want you to get them out and I want you to read them. I want you to understand there would have been two types of mass spectroscopy we covered. Type 1 is electron impact. That's where high energy electrons from a hot filament are accelerated, and as they accelerate they smack into the unknown chemicals and they knock out, hopefully one electron knocks out another electron and you get the positive ions being formed. Those positive ions are accelerated and they're deflected and they're detected. I don't want to go through all of that again, but I hope you remember that. But the more recent, the more used nowadays, more recent advances in mass spec have led to electrospray ionization. If you remember what that was getting a thin needle and it's throwing your sample down the needle so it sprays out at the end. The end of the needle is highly positively charged, and what that does is if you've got the solvent and the unknown, what comes out is the unknown in droplets with the solvent, and as the solvent evaporates away, it will leave the molecule with a proton, the molecule with a H plus extra to the molecule, and that molecule with a H plus extra will then undergo ion drift through a tube of a certain length, and it will register. When it hits the end, there are detectors at the end. As these things hit the end, then they register. Essentially, the two techniques are both within AQA chemistry, and you need to know both of them. So go back, revise them. But having revised them, then can I just remind you of what those techniques gave us? And those techniques gave us information about, if it was elements, they gave us information about atomic mass, or if it was a molecule, they gave us the information about relative molecular mass. So relative atomic mass, relative molecular mass is whether you're dealing with elements or whether you're dealing with compounds. Those fed in to the machine would give us, once we know that something is a relative molecular mass of 56, we know it's a hydrocarbon, then we can start piecing together how many carbons, how many hydrogens must be there in order to make it up. So if you know the MR value or the AR value, that you can go a long way to answering the questions on exams. Well, with elements, I think back in year 12, we used it to work out the relative atomic mass by looking at the relative height. Each isotope will give a different peak. You looked at the heights of the isotopes, you worked out the relative amounts of each isotope, and then you did a weighted average calculation. So before I get on to year 13 work, let's have a look at these things. The example I've got here is magnesium. So magnesium, my example. If you remember, the charge of one positive charge, that's the charge Z of 1, then these numbers will represent the mass over charge ratio. The charge is 1, the numbers are mass. So magnesium atoms that weigh 24 units with charge of 1 plus 24, there are 79% of them. If you measure that height, and that is 79% of that height, add that height, is 100%. So 79% of them are magnesium 24, and when I got this diagram off the internet, there were no plus charges, positive charges on it. I want you to label the ions that you get as positive. They have to be positive, otherwise they would not get through and hit the detector. Without them being positive, it makes no sense. So I want you to put positive in. This is magnesium atoms with mass number of 24, positively charged ion. And this one is mass number 25 magnesium ions. And this one is magnesium 26. We say magnesium 26, magnesium 25, magnesium 24. We know the relative abundances from the heights. All the ions are positive. And then you can do a calculation like I've just scrolled it on the same slide here to remind you. The magnesium, the weight 24, out of every 100, and that's the way I want you to think about your weighted average calculations, is if you've got 100 typical atoms, then divide by 100 to get the average weight of one of them, but write the weights of 100 on top. So 79 of them weigh 24, add 25 of them weigh, 10 of them weigh 25. 10 of them weigh 25, 10 times 25. 11 of them weigh 26. 11 times 26 over 100, and I got an answer of 24.32. So the relative atomic mass of magnesium is 24.32. No units, because it's a relative term. Now that kind of calculation you did in year 12. So, having recapped year 12 work, very quickly I've done it, I want you to go through in more detail, then let's move on to what's new for year 13. Well, what's new is, year 13 you have to deal with molecules. So not just individual atoms, this is magnesium atoms, 3 different isotopes. At A level, year 13 is where atoms are joined together as a whole molecule. Now let me define a molecule. If you remember, molecules are collections of atoms covalently bonded together. And that means that you're going to have whole molecules. And imagine doing mass spectroscopy with whole molecules. Will the same thing happen? Well, electron bombardment, yes. You knock out an electron, you get the whole molecule positively charged. Electron spray, as you spray it out, you get the whole molecule with a H plus charge. So the whole thing is one hydrogen with a molecule all 1 plus. And therefore they will show through the mass spectroscopy machines, whether they happen to be electron impact or whether they happen to be electrospray ionization machines, they will still work their way through because they're positively charged. So if we look at now molecules, then what's extra is that apart from just the molecular ion, the whole molecule going through as being positively charged, or the whole molecule going through and having an extra proton in electron spray mass spectroscopy, then the extra thing that can happen is the molecule can break up, it can fragment. So if we've got a molecule, say pentane, 5 carbons long, then maybe there's a fragment, maybe a piece can break. 2 carbons can break off as an ethyl group and the other 3 carbons as a propyl group. Provided one of them is positively charged, then it will show up and we'll see it. So the extra thing we see is we see fragments. And the fragmentation is something that can cast great light on the structure of the unknown that we've got. If we know the fragments, then we can put the fragments kind of together, a bit like a jigsaw, and work back to what the structure was overall. So we can get some useful information, but the technique that does this fragmentation largely is electron impact. Electrospray is a soft kind of ionization, and we get very little fragmentation. We do get fragmentation, but we don't get very much. So if you want to look at fragmentation patterns, then we tend to use the electron impact type machines rather than the electrospray machines that are more modern machines. So have I covered these things? If you've got a molecule and it's going to fragment, where is it going to break up? Which bonds are going to break? Well, it's the weaker bonds. The weaker bonds present are the ones that are likely to break. So carbon-carbon bonds break rather than carbon-hydrogen bonds, which are a stronger bond. Similarly, double bonds are stronger and they're less likely to break. One other thing, if you've got a molecule like PQ, P, this fist P, this fist Q, PQ joined together, and you break it, the shared pair of electrons, the group P and the group Q, if they are covalently bonded, have a shared pair of electrons. The shared pair of electrons has to go somewhere. Now, wherever it goes, that portion, that fragment, will be negatively charged. So, molecule like PQ, turning into a P ion and a Q ion, one of the ions has to be positive, one of the ions is negative. Now, in a mass spec machine, only the positive ion will make its way through and show up. The negative ion will not go through the machine and hit the detector. So we only ever see, when bonds break, we only ever see the fragment that is positively charged going through the machine and hitting the detector and showing up as a peak on our mass spectrum that we will analyse later. People showing the Q fragment will not. Let's look at some samples. Examples. Right, so 2-pentanol. Can you see the heights represent abundances? So the taller the peak, the more of that we've got. The shorter the peak, they've got a tiny amount of it. The y-axis, M over Z, is mass charge ratio. You're hoping that the Z is 1. If the Z is 2, then the numbers would be half these values. Occasionally we get tiny peak at half the value we expect, and that's because the charge is 2 plus and not 1 plus. But the majority of the ions are 1 plus, and therefore we can go about trying to identify them. Now, this was the sample, 2-pentanone, and what I've done is I've tried to identify the peaks for you. So that the first peak to look at is the last one. The last one is the molecule. Now, the molecule being positively charged, molecule plus, and the molecule plus is 86. Now, if you add up here, that's a CH3, which is 15, CH2, 14, CH2, 14, a carbon there and an oxygen there, 12 and 16, and a CH3 there, which is 15. If you add up all of those, they add up to 86. So 86 is when the whole molecule has gone through, and I want you to label it with a positive charge. The whole molecule as a positive charge. I could put brackets around that and label it, top right corner, label it with a positive charge. That's what that peak would be. Well, let's try and identify some of these other peaks. Well, there's a peak here at 15, 12 and 3, CH3 plus. That is a fragment. So if the bond breaks, if that bond breaks there, then this CH3, the CH3 will show up as a fragment CH3. What if that bond breaks there? Then C2H5, CH3, CH2, C2H5 would show up, if you add those up, at 29. And I think that is 29. I find it hard to read these diagrams sometimes with my reading glasses. This big peak though, big peak. Well, the big peak will be CH3, CH2, CH2. CH3, CH2, CH2, 43. 3 carbons, 36. 36 add 3 and 4 makes 7. 36 add 7 makes 43. So put it all in a bracket and put the positive charge in the top right hand corner. These are positively charged ions. See, positive charge. And then let's work backwards. If this is the molecule and this is 71, how much smaller is it? That is 15 smaller than 86. So that's the molecule minus, that red line is a minus, not a bond. That is the molecule less a CH3 group. So it's like all of that if you lose that. Or all of that if you lose that. If you take off a CH3, then that's that peak there. Now, 58. I couldn't work out what would give me a peak of 58. I was breaking things and I couldn't quite, I got to 57, but perhaps you can work out what that peak of 58 is. I just put a question mark and I'll leave it to you for you to think about. Right, next one. This is 2-chloropropane. Now, 2-chloropropane, I've drawn it. That's 2-chloropropane there. If you work out the MR value of it, 78, look, 78 is this peak here. 78, that peak there. Look at that peak at 80. So, now you've got to use your common sense and your intelligence and your chemical nous to answer these kind of questions that require a little bit extra thinking. Not much extra thinking, but a little bit extra. Now, chlorine. You should know chlorine comes in 2 isotopes, chlorine 35 and chlorine 37. If you don't know that, you need to learn that. That should be part of your chemical general knowledge. Now, if that 78 is with chlorine, when chlorine is 35, this 80 will be that molecule when the chlorine is chlorine 37 isotope. So having that molecular ion completely, these two represent the molecular ion, positively charged. This one is with a heavier isotope of chlorine, and that's with the lighter isotope of chlorine. Both of them are the molecular ion. So what's that peak there? Well, that is 15 less. 15 less than this is like 63, and the molecule, a CH3 less. So if you lost that, there, then that would be one solution for that peak there. And of course the 2 along is the heavier chlorine version of the same fragment. But all these are fragments. Well, this peak, if you take 78 and take off 35, 78 take off 35 would be 43. And that's 43, big peak. So losing the chlorine is something that happens quite well here in this electron impact. The chlorine gets broken off, presumably because the carbon-chlorine bond will be a weaker bond than the carbon-carbon bonds and the carbon-hydrogen bonds, and so it's more likely to break. So you can identify the peak there. Let's try and deal with, where would you see, if that broke off, chlorine breaks off, where would you see it? Well, you see it at 35. 35. 35 is there. No peak at all. Why don't you see chlorine 35? Well, because that doesn't form. What forms when that chlorine breaks off is the chlorine takes the 2 electrons with it, and it comes away as chloride negative charge ion. And as I said, you're not going to get negative charge ions showing through on a mass spec. So Cl- won't show through. It's only the positive charges that will show through. So be mindful. Only positive charges, and be mindful of isotopes. Isotopes will give you little peaks, or they might not be so little. In the case of bromine, the 2 isotopes are the same abundance, so the isotopic peaks are the same height. So if you've got peaks nearby and they want you to talk about them, always think about it might be an isotopic version of the same fragment, etc. Okay, so the next example I'm going to do with you. Next example was, I got this off the internet simply because the M/Z values are huge. Now, the really big M/Z values, that means the RMM, the relative molecular mass, is huge. And what's got a huge relative molecular mass is, I would say, proteins. Now, proteins have these kind of numbers. So, if you've got protein, that is a very large number. It's larger than 1600 is where my finger is. It's larger than that. About 1600 I've written, very large. And that's the whole protein molecule with 1+ charge. And molecular ion, the whole protein structure, 1 positively charged. But then what are all these? Well, I would say they're fragments. They are fragments of this protein. Now, as I taught you in previous videos, you can break a protein down into the amino acids that originally made it up through a process called hydrolysis. So, in that way, perhaps, the peptide links have been broken by electron impact. As they've been broken by electron impact, then that chain of amino acids breaking away, chains breaking away so that the links like amino acids are falling off, will lead to a protein, the remnants, the fragment, being smaller and lighter. And that will show up at lower values. And you get various peaks showing up at lower values, which I think will be down to that protein breaking up and its structure breaking up into smaller and smaller pieces, perhaps amino acids breaking off, etc. Next. Now, one very common thing is to talk about chlorine. So I've here got just chlorine, the mass spec of chlorine molecules, Cl2, diatomic molecules. Now, the diatomic molecules we know from our chemistry back in year 9 onwards, that 3/4 of chlorine atoms are the lighter 35 type. And 1/4 of all chlorine atoms are the chlorine 37, the heavier type of isotope. 2 isotopes. If a chlorine molecule fragments into pieces, it's going to fragment into chlorine and chlorine. The chlorine plus, 35 chlorine plus, will show up at chlorine 35, M over Z value 35. Chlorine 37 atoms, where they've got an electron removed, now existing as ions through the machine Cl+, this chlorine 37 will show up at value 37. What's interesting is up here, because you've got 3 peaks. Now they're the molecules. They are this chlorine. They're the molecules of chlorine. Now, if the first chlorine were a chlorine 35 and the second chlorine was a chlorine 35, then you'd get together the Cl+. You see I've put a plus there? You must put it in. The positive charged molecule weighing 70 M over Z. Right, what if one of those chlorines was a chlorine 37? Then it would have 2 units more. So that would be 72. And see the peak there. What if both of the chlorines were the heavier type? 37 and 37 would show up at 2 more units along here. So that would be 74, this would be 72, that would be 70. What's even more interesting is the ratios. If you're into mathematics and probability, the ratios are 9 to 6 to 1. Of that peak to that peak to that peak. And that's entirely down to the probability of chlorine joining together. Because the chance of getting at random a chlorine that's the lighter one is 3/4. The chance of getting a chlorine which is the heavier one is 1/4. So, to get 2 light chlorines is 3/4 times 3/4, which is 9/16. The chances of getting this one, which is heavier one, 1/4 times 1/4 is 1/16. So you can see that this one would be 1/16 the height of that one. No, I've said that wrong, sorry lads. Let me just go back to that. The chance of getting a chlorine 35 is 3/4. The chances of getting a chlorine 35 and a chlorine 35 is 3/4 times 3/4, 9/16. So that one is 9 times as high as this one. The chances of getting a heavier chlorine with a heavier chlorine, 1/4 times 1/4 is 1/16. So this will be 1/9 the height of that. So it's clear that is 1/9 the height of that. Where boys find it difficult to think about is the middle peak being in ratio 6. And you get that as follows. If you've got the first chlorine as 35 and the second chlorine as 37, then it's 3/4 times 1/4 is 3/16. But then the other way around, you could have the first chlorine being chlorine 37 and the second chlorine being chlorine 35, and that would also be 3/4 times 1/4, which would be 3/16. So 3/16, there's a chance of getting that way around. 3/16 is a chance of getting that the other way around, and therefore the total chance of getting something that weighs 72 is 3/16, add 3/16, which is 6/16. So the ratio would be 9 to 6 to 1. I hope you understand that, but I don't think that's ever been asked. It's in all the books and you can go on the internet, etc. But I think mathematically, I think that's perhaps just a step too far for some people and they don't ask about it. So that is that's the end of Mass Spec. I think my next video I'm going to deal with infrared. See you then.